going to skip 4 for a minute and come back to that later because I've got the practical kit set up for star connected system. So what we're going to look at now is the balanced star and what happens when we get a loss of line fault in that system. So load is connected in star as per problem 2, developed a fault where one line has gone open circuit. Sketch a diagram of this faulted system and determine the current flowing in the remaining lines, the new power dissipated by each load, the new total power dissipated by the system under fault conditions, comparing with problem 2, and the current flowing in a neutral conductor. Yep. So off you go and create a diagram of that, but with, let's say, the blue phase has become disconnected. With this one then. Think we've done it? So essentially what we got here, where are we looking at current flowing in this circuit now? Yeah, it's going to go, pick a nice colours. We've only got one path for current now, and that's up there, round there, and along that wire there. There's nothing flowing in R3. Yeah? So how have we calculated the currents IR and IY then? Yeah, so IR yeah, you've done that, have you? Can you see any other way you could tackle this? What could you say about those two currents now? Yeah, they are the same. Yeah. So you're going down this BR over root 3. Why have you done root 2? No, you can't do that. That's still over this end is still a 3-phase generator connected in star, right? And that's going off to your load. Your neutral is connected to there, right? The 300 volts, remember, is there to there. It's the line voltage, right? So this bit here to here is still 300 over root 3. That root 3 is nothing to do with the fact there's 3 of them. So you don't go down to square root of 2 when there's only 2 phases. Stays as is. Okay? Yeah? So that's still 300 volts between there and there. In theory, of course, on a real system, depending on how big the source is, I mean, if you're talking about Sizewell, one load going open circuit ain't going to make a major difference unless that's one phase of, I don't know, a big city like Norwich completely gone. That would make a difference. But one phase of your motor going open circuit is not going to make a difference. Do you see what I mean by that? So in reality, yes, that would make a slight difference to that load, but in theory, it doesn't make any difference. Still 300 volts there. So we've got the full ER over root 3 divided by R1. So pause. There you are. Just to clarify that issue, when you draw the phasor diagram, if we look at these two phases, EA and EB, they add together in the fact that it's EA minus EB because they're in opposite directions, the arrows are. Yeah. So we draw a phasor diagram. There's EA pointing straight upwards. Put the magic pen on for the video watcher. EA pointing straight upwards. EB is along there, so minus EB is up there. Those come to make that parallelogram, and then so we get this sine rule thing there. EL over 1 sine 120 is equal to E phase over sine 30. Rearranged, the line voltage is equal to E phase times sine 120 over sine 30, and if you do sine 120 over sine 30 on your calculator, you'll find that the answer is √3. So that's where it comes from. So it's nothing to do with the fact, it is to do with there's 3 of them, but it's more to do with they're out of phase with each other than it is, because the phase voltage is not 3 times the line voltage. It's not a third of the line voltage, is it? That's √3. Yeah? So hopefully that has that cleared that up. Yeah? Right, gents. So now we've clarified what we're talking about in terms of the line voltage. IR is ER over √3 divided by the resistance. So the values are there. 300 over √3. R1 is 1950. And the answer to that is 88.8, isn't it? Yeah. Milliamps, angle 0 degrees. So that's angle 0 degrees as well. Completeness. Yeah. R2, same value. Therefore, I2 must equal 88.8 milliamps, angle 120 degrees. Yeah, that's absolutely fine to use that and use your knowledge to say they're both the same value, the 2 voltages should be the same, therefore it's a balanced system, therefore that current should be the same, but the angle is different. Yeah, okay. So that's the current. What about the P phase, or PR1? The power in both of them is going to be the same. PR1 is equal to PR2 because they're both the same value. They've both got the same current flowing through them. So how have we done that? IR squared times R, that's 0.0888 squared times 1950 equals how does that compare with the phase wattage from problem 2? So, same as problem 2. Yep. New power dissipated by the system under fault conditions. So the new total power, PT, must be PR1 times 2, that's 30.8 watts. How does that compare?
16 watts less.
Problem 2 was 46 something, wasn't it? Approximately 46 watts. So it's about a third. So you drop one load in star and you got about a third the power you had. So in terms of that power thing, that's balanced. You lose one load, you lose 1/3 of your power. Yeah. Let's write that down. 1/3 less. Overall. Okay. And the last bit was neutral current. D by Kirchhoff's current law, IN I1 plus I2 I1 is 88.8 angle 0 degrees, 88.8 plus 0J, I2 what did that come out as? Minus something, wasn't it?
Minus 44.4 plus 76.9.
Add them up, that's 76.9. This is 44.4. What did that convert back?
8 milliamps into 60 degrees.
88.8 milliamps, angle 60. Yep. Okay. So, we'll take a look at that practically in a minute, alright, and confirm that that's that's what we get. What I'm going to leave you with is having a go at the three-phase balanced delta with loss of line faults. So the same thing, we'll say we'd drop the blue phase from the supply, okay? Have a go, see if you can do a similar analysis of that. It's a little bit more tricky than the star one with the fault removed. Maybe once you've drawn the diagram of the whole system, just take out what you've got connected, lose all the other stuff, and that might look a little bit simpler then. So draw it in a more conventional way might be helpful. And then we'll analyse that next week and test that on the system as well. Okay, so I'll get set up over there and I'll just show you these currents flowing and confirm them, and then I'll leave you to finish off by having a go at that problem.
I've got a quick question about that last question.
Yeah.
We all dropped the same phase.
Yeah.
If we dropped one of the other phases rather than the blue, would we still get the same answer?
You'll still get the same magnitude.
60.
The angle will be different.
So we still get 88. Okay. Yeah.
I believe.
Might not be 60 degrees.
Yeah, because if you look at this arithmetic down here, if you dropped the yellow phase instead of the blue, this would be minus 120, which would make that minus, so that'll be minus down there. Yeah? Alright? That's the crux of it, isn't it? Because we know when we done the full three phases, we had 88.8 and nothing, minus 44 and plus 76 and plus 44 and minus 44 again and minus 76. So that sign doesn't change, but this changes sign. So therefore we get an opposite, we get an angle over in the other quadrant. Yep. So the angle will be different, but the magnitude will be the same. and that would be the case even if we drop the the red, we'd have 88 positive 120 degrees and 88 negative 120 degrees. These two will both be minus 44.4. Yeah. Okay. But the angles would mean they add up to something.
So your answer does change.
Yeah.
What case?
Yeah. The angular result's going to fall between two of the other angles, isn't it? So you'd have one at 180, and then you'd have one at 240, halfway between 240 and 360. Yeah. Okay.
Yeah.
Do them if you don't believe me. You got all the results. You got all three results. Just pair all of them up and see what answer you get. And the magnitude will always be the same, but you'll get three different angles for the neutral current. All right.